Okay, so I'm sharing my desktop there. You see my slide?
Yes.
Okay, let's see Okay, so I'm Shinya Narita of Iwate University in Japan. So today I'm showing our studies on the heat measurement in hydrogen desorption experiment using the palladium foil coated with nickel membrane. Oh yeah. Okay, let me start with some background of this study. And the gas phase experiment has advantages in accurate measurement of the sample temperature and radiation measurement in case of low gas pressure and searching for the transmutation products with the high purity gas. So in such gas phase experiment, and some significant results have been obtained recently. So here there are excess heat has been observed in the hydrogen deuterium loading with non-composite particles and non-sized multi-layer composites such as palladium, nickel, and nickel, palladium, and palladium sandwiched with the gold and silica. And some results are shown. You can see some results in these references. So from these results, considerable conditions for inducing a reaction as a source of the excess heat generation has been suggested. So as for the sample composition and structure, the metal composites such as the composite particles and multi-composite layers has some important key to induce a reaction. Also, the nanostructure such as nano-sized particle and the thin membrane is seem to be effective for the reaction. And for reactant, both hydrogen and deuterium are effective. And concerning the gas temperature, high temperature gas seems to be the better. It is suggested. Yes. Okay, so considering these conditions, we have conducted the hydrogen and deuterium desorption experiment using the palladium foil coated with the metal membrane, such as the palladium nickel and palladium zirconium, and something like these samples. And we examined the thermal and deuterium diffusion behaviors. Then we observed anomalous heat evolution in the hydrogen and deuterium diffusion process. And we think the study with the various types of sample may help specify the condition for inducing the phenomena and clarify the reaction mechanisms. So some of our results are also shown in these references. And now recently we have the modified experimental setups so that the experiments can be conducted under constant experimental conditions. So here in this study, we have performed a hydrogen desorption experiment using a sample of palladium foil coated with the nickel membrane, also called palladium nickel sample, and investigated thermal as well as the hydrogen diffusion behaviors. Then the excess heat was estimated. Okay, so I am showing our experiments. So first of all, the hydrogen loading. Oh no, I skipped one slide. Oops. Yes, starting with the sample preparation. We use the palladium foil with the size of 10 millimeter square and the thickness of the 0.1 millimeter with the purity of the above 99.95%. And at first we annealed the sample at the 900 degrees Celsius for the 10 hours. Then we removed the surface contaminants by the acrylasia. And fine structure was formed on the surface of the palladium foil by etching with an argon ion beam. As I showed in the previous slides, fine structure of the sample is supposed to be one of the important conditions for inducing the phenomena. That is why we form the fine structure on the surface. So here the microscopic images for the sample surface after etching. So this is the AFM atomic force microscopy image. So you can see the projected shape with the width of 2 micrometer and height of about 20 nanometer, like this. And more detailed image taken by the transmission electron microscope. Then you can see some semi-spherical shape of the 5 to the 200 nanometer here. So in a preliminary experiment, the heat evolution phenomena was observed more efficiently with this fine structure. So in our previous experiments, we tested the sample without this fine structure, but this fine shape seems to be effective. Then after that, on the surface, nickel membrane was deposited on the surface. So this is a sample structure. Okay. Yeah. And then hydrogen loading. So this is a setup of the hydrogen loading system. This is a loading cell. Then we put the sample here. Then after evacuation of the system, the hydrogen introduced in the cell with the pressure of the 5 atm. Then the sample exposed for 24 hours. Then the weight of the sample measured before and after loading, then the loading ratio, or so-called H over the palladium, was calculated from the weight difference. The typical loading ratio was 0.7 to 0.8. And here I should note that this loading ratio, this value is averaged over the entire sample, and it may be much larger locally. Okay, so then the desorption. So this is the desorption setup. The sample was set into the chamber here. Then it was evacuated to the about 10 to the minus 4 Pascal. And then the direct current at constant power of the 0.6 watts was applied to the sample to stimulate the hydrogen desorption by the Joule heating. Well, actually, we formerly used the constant direct current power supply, but now we use the constant power supply instead. Yeah, this is one of the modifications of our experimental setup. So then the sample temperature was monitored by a thermocouple and the infrared thermometer, and the pressure in the chamber and the voltage current applied to the sample were also monitored. And the desorption experiments were usually conducted for 24 hours. So this is some details of the sample holder. Sample is fixed here, and electric power was applied through this point contact. Then the temperature of the sample was measured by the thermocouple here and the infrared thermometer here. And here you can see the camera, and the sample was monitored by the camera through the viewing port. And during the desorption experiment, I'm showing more details on this later. Okay, so this is the result. Okay, so this is a typical behavior of the temperature and pressure. So upper plot is for 24 hours from the beginning of the desorption experiment to the end of the experiment. So this yellow plot shows the temperature measured by the thermocouple, and red one is measured by the IR thermometer, and this blue line shows the pressure inside the chamber. Then this green one is the supplied power to the sample. So now the supplied power is constant. So you can see some fluctuation of the periodic fluctuation of the supplied power, but we have understood this. This is due to the noise of the logging system, not the real electric power fluctuation. Okay, so the bottom plot is the enlarged plot of the first 4 hours. Again, the temperature and pressure and the power supply to the sample. And now we found the sample temperature increased just after the constant electric power was supplied. So here and here, yes, so this is by the Joule heating. And after that, intermittent temperature increase that occurred simultaneously, concurrently with the pressure behavior here and here. And of that, it happened approximately 0.5 hours after the beginning of the experiment. And the phenomena continued for about 0.5 hours. So it seems the heat evolution was induced when the hydrogen was dissolved. Then thereafter, the temperature did not change significantly. So now we suppose that hydrogen was fully dissolved from the sample in that period. And note that there is a difference in the indicated temperature between the thermocouple and the infrared thermometer. So this is considered to be due to the difference in the time response and maybe imperfect of the calibration. Okay, so since the hydrogen desorption from the palladium is the endothermic, so the heat evolution is not due to the desorption heat. So, and some intermittent temperature increase happened concurrently with pressure increase, and as I said, and it suggests the heat generation reaction might be related to the hydrogen diffusion. So now, for example, the following diffusion model is possible. So hydrogen atoms move to the sample surface, and hydrogen densified locally and dissolved from the sample when the density exceeds a certain level. Then at that time, the heat evolution happened at that time. Yeah, this is just a more possible model and just a speculation, but yeah. Okay, so now we could imagine the heat generation reaction occurred in this high densified state. But then another notable aspect of this result is that this phenomenon occurred at not so high temperature. It happened below 100 degrees Celsius. So it has been indicated excess heat generation occurs more efficiently at higher temperature by the other experiment in gas phase other experiment. So such experiment, excess heat was observed have been observed at several hundred degrees Celsius. So comparing that, in our case, the temperature increase happened in the relatively lower temperature. So similar temperature pressure behaviors have been observed with good reproducibility and time of occurrence and increased behavior of the temperature differs by sample, but all of the phenomena occurred within the 4 hours of the start of the desorption experiment. Yeah, I put the result of the 4 experiments, 4 runs. So for each case, you can see the temperature increase with the pressure increase here and here and here. And these phenomena have been observed in all 9 experiments we have conducted so far. So with good reproducibility, we have seen that. Okay, so now, then from these results, we have preliminarily estimated the excess power from the temperature behaviors. So here's the procedure to estimate the excess heat. Okay, so at first the calibration experiment was performed to determine the correlation between the supplied electric power and the temperature change. So this left plot, this is an example for the calibration. We examined how much temperature increased when the supplying the given power to the sample. So then we have obtained the calibration data from the sample, the relationship between the delta P to delta power. And the power evolution was calculated from the temperature behavior in the desorption experiment using this calibration data obtained, as I said, I showed. Then we consider the behavior for the unloaded sample. So this is the temperature and the pressure behavior for unloaded sample. So now you may not see a specific change in temperature. I mean, this yellow and red one are the temperature for thermocouple and IR respectively, and you may not see any increase in the temperature. Also, you may not see the pressure increase either. These spikes are the noise of the monitoring system. We have understood that. So the power evolution for this unloaded sample was measured with the temperature behavior in the same way as above. Then the excess heat was calculated from the difference of this 2 and 3, the desorption experiment, difference for the desorption experiment and for the unloaded sample experiment. Okay, so now this is the estimated excess power.
5 minutes.
5 minutes, okay. And this middle one is the excess power estimated by the thermocouple measurement, and this right one is from the IR, infrared thermometer measurements. So now we can see the instantaneous excess power was estimated to be the 0.2 or 0.3 watts, 200 to 300 milliwatts, here and here at maximum. And we found that the fluctuation of the baseline is not so small, so there is a certain level of ambiguity in the estimated value. So this is one of the issues to be considered to be resolved in the next step. Yeah, we understand it is the important thing that. And there seems to be another ambiguity in the evaluation in the transitional period, so difference between the results from the thermocouple of the infrared thermometer results. So, as I mentioned before, one of the reasons might be the difference in the time response. And also, we should keep in mind the uncertainty of the reference experiment significantly affect that result. So we should take a look at the carefully for the reference result. Okay, so these are results for other runs for 3 runs. And the top 3 plots by the estimated excess heat by the thermocouple measurement, and the bottom 3 are the excess heat by the IR thermometers. And now you can see the same order of the excess heat, a few hundreds milliwatts. And also we should note that the result with off-baseline, this experiment, you can see the off-baseline there. So we suppose the reference may not be appropriate for this round. Okay. Oops, I skipped this round. Okay, so another interesting topic is observation of sample deformation simultaneously with the heat evolution. The phenomenon was originally reported by the Yamaguchi et al. And they conducted similar experiments, similar desorption experiment using the multi-layer palladium sandwiched with gold and silica. And they found the sample deformation, and the deformation is considered to be caused by the internal stress generated by the diffusion of hydrogen in the sample and the enrichment of the sample method. So a model has been proposed which the phase transition of the sample results in localized densification of the hydrogen in the sample, and then the causing the reaction. I don't know it is not nuclear or not, but any reaction. So that's the reason why we put the camera and we to observe the sample behavior sample deformation during the desorption experiment. So this is an image of the sample before and after heat evolution. There it is hard to see the sample itself. So now I put some drawing here. So before and after the heat evolution, the nickel side exhibited convex deformation before and after the heat evolution occurred. And but actually this deformation was observed in the samples subjected to the excess heat, but not all samples. So this result may be related to the hydrogen diffusion model discussed earlier, and it may also provide. So this may also provide a hint for the understanding how the exothermic heat evolution is induced. Okay, in summary, we have performed a hydrogen desorption experiment with palladium foil coated with nickel membrane. We found that we observed an intermittent temperature increase that occurred concurrently with the pressure behavior at early stage of the experiment. And the phenomena happened at low condition below the 100 degrees Celsius, and we have preliminarily estimated the excess heat from the temperature and found it to be few hundred milliwatts, but it is still preliminary, so we should consider carefully for the ambiguity in the estimation. Yeah, the accuracy of the temperature measurement as well as the excess heat calculation need to be improved, improve accuracy of the calculation data, and reduce the uncertainties in the reference experiment. And sample deformation has been observed before and after the heat evolution. It may be related to the model proposed as a reaction-induced process. Okay, that's all.
Okay, thank you very much. Almost no time left, but I just cannot
20
say.
seconds.
20 seconds.
Yes.
Exactly.
What was the mass of the sample, please?
Mass of the sample. So we use the palladium foil with the size of the 10 millimeter square with the thickness of the 0.1 millimeter.
Okay, so I'll have to multiply by density to figure it out.
Yes.
And how much was the increase after you loaded? Like, what's the temperature, the mass difference before and after?
it's still below the 100, just 20 or 30 degrees.
No, sorry, the mass, not the temperature. You said you determined the loading ratio by mass?
Yes.
So what was the delta in mass after loading?
After loading, I'm sorry, I don't have the number for now. I'm sorry, exact number. But anyway, we measure the mass with some precise weight measurement system. So
I have a
I'm sorry.
question. Yes,
Just a second.
I have one last question. Why did you put the nickel on top of the palladium? Why without? Did you do it without nickel also?
Yes. So in that case, we don't see the this kind of the temperature increase.
Okay, thank you very much.